Did you know that finding the area under the curve of cosecant squared of x is simpler than you think? In fact, there's an elegant formula that makes this integration straightforward. But what exactly is cosecant squared of x? Let's start with the basics. Cosecant squared of x is simply 1 divided by sine squared of x. This function has a very distinctive shape. It approaches infinity wherever sine of x equals 0, creating vertical asymptotes at multiples of pi. Between these asymptotes, the function creates smooth, U-shaped curves. Now, when we talk about integrating cosecant squared of x, we're essentially finding the area under this curve. This integral appears frequently in advanced calculus, physics problems involving oscillatory motion, and engineering applications. In the upcoming sections, I'll show you 3 different methods to evaluate this integral. We'll start with direct recognition, then explore substitution techniques, and discuss important domain considerations. By the end, you'll have multiple tools to tackle this integral with confidence. Here's the fundamental result we need to understand. The integral of cosecant squared of x equals negative cotangent of x plus c. Let's break down each part of this integral to understand what it means. The integral symbol tells us we're finding the antiderivative. Cosecant squared of x is our function. The result is negative cotangent of x, and c is the constant of integration. The constant c is crucial in indefinite integrals. Since derivatives of constants are 0, when we reverse the process through integration, we must add this arbitrary constant. Think of it this way. The derivative of any constant is 0. So when we integrate and reverse this process, we must account for any constant that might have been there originally. Now here's the key insight. Cosecant squared of x is actually the derivative of negative cotangent of x. This is why the integral works. The derivative of negative cotangent x equals cosecant squared x. This fundamental relationship is what makes our integral formula work. Integration is the reverse process of differentiation. Since we know the derivative, we can work backwards to find the integral. This is a fundamental integral that you should memorize, just like knowing that the integral of cosine x is sine x. It's one of the essential building blocks of calculus. Make sure to commit this integral to memory. It will appear frequently in your calculus studies and is essential for solving more complex problems. The most efficient method for integrating cosecant squared is direct recognition. This means recognizing that cosecant squared is actually the derivative of negative cotangent. We want to find the integral of cosecant squared of x. The key insight is to think backwards. What function has cosecant squared as its derivative? The key insight is to think backwards. Instead of trying to integrate directly, we ask, what function, when differentiated, gives us cosecant squared? Let's check the derivative of negative cotangent. Now we'll calculate the derivative of negative cotangent step by step. This will show us exactly why the integral of cosecant squared equals negative cotangent. First, we factor out the negative sign. The derivative of negative cotangent equals negative times the derivative of cotangent. Now we need the derivative of cotangent. From our trigonometric derivatives, we know that the derivative of cotangent x is negative cosecant squared x. Simplifying, negative times negative cosecant squared gives us positive cosecant squared. Perfect. This confirms our pattern. Now that we've verified the derivative relationship, we can state our integral result with confidence. Therefore, by the fundamental theorem of calculus, since the derivative of negative cotangent is cosecant squared, the integral of cosecant squared must be negative cotangent plus the constant of integration. The key skill here is pattern recognition. By memorizing that the derivative of negative cotangent is cosecant squared, you can instantly solve any integral involving cosecant squared. This is much faster than using substitution or other methods. This direct recognition method is the fastest and most efficient way to handle integrals of cosecant squared. Practice recognizing this pattern, and you'll solve these problems in seconds rather than minutes. Now we'll explore the substitution method as an alternative approach to finding the integral of cosecant squared x. While this method takes more steps, it helps us understand the deeper relationship between cotangent and cosecant squared. Step 1. We begin by choosing our substitution. Let u equal cotangent of x. This choice might seem unusual at first, but it will reveal the connection between these trigonometric functions. Step 2. Now we need to find du. We take the derivative of both sides. The derivative of cotangent x is negative cosecant squared x, so du equals negative cosecant squared x dx. Step 3. This is the key insight. We can rearrange our equation to solve for cosecant squared x dx. If du equals negative cosecant squared x dx, then cosecant squared x dx equals negative du. Step 4. Now we substitute our expression back into the original integral. The integral of cosecant squared x dx becomes the integral of negative du, which is much simpler to evaluate. Step 5. The integral of negative du is simply negative u plus our constant of integration. This is one of the most basic integration rules. Step 6. Finally, we substitute back our original expression. Since u equals cotangent x, we replace u with cotangent x to get our final answer, negative cotangent x plus c. Therefore, using the substitution method, we arrive at the same result. The integral of cosecant squared x dx equals negative cotangent x plus c. This confirms our answer and demonstrates the beautiful relationship between these trigonometric functions. While the substitution method requires more steps than direct recognition, it provides valuable insight into why this integral works. It shows us that the derivative relationship between cotangent and cosecant squared is fundamental to understanding trigonometric integration. When working with the integral of cosecant squared, we must be very careful about where these functions are actually defined. There are specific points where both cosecant squared and cotangent become undefined, creating gaps in their domains. The root of the problem lies in the definitions of these trigonometric functions. Cosecant is defined as 1 over sine x, and cotangent is cosine x over sine x. This means both functions become undefined whenever sine x equals 0. Sine x equals 0 at specific predictable points, at 0, pi, 2 pi, 3 pi, and so on. In general, sine x equals 0 whenever x equals n times pi, where n is any integer, positive, negative, or 0. Now let's visualize what this means graphically. I'll show you the graph of cosecant squared x, which has vertical asymptotes, infinite spikes, at each point where sine x equals 0. Notice the vertical asymptotes at x equals 0, pi, 2 pi, and so on. The function shoots up to infinity at these points because we're dividing by 0. Between these asymptotes, the function is continuous and well-defined. Similarly, the cotangent function also has vertical asymptotes at the same x values. Let me show you the graph of negative cotangent x, which is our antiderivative. The negative cotangent function also has vertical asymptotes at the same problematic points. Between asymptotes, the function is continuous and decreasing. This is why our integral is only valid on intervals that don't cross these asymptote lines. This brings us to a crucial concept: valid integration intervals. When we integrate cosecant squared, we can only do so over intervals where the function is continuous, that is, intervals that don't contain any asymptotes. Here's what you need to remember. You cannot integrate across an asymptote. For example, trying to integrate from negative pi to pi would be invalid because it crosses the asymptote at x equals 0. In practical terms, this means when you're setting up definite integrals involving cosecant squared or cotangent, always check that your limits of integration don't include points where sine x equals 0. This is essential for getting correct finite answers. Now we'll work through a concrete example to see how to evaluate a definite integral involving cosecant squared. We need to evaluate the definite integral of cosecant squared x from pi over 6 to pi over 4. Step 1, we apply our antiderivative formula. Since the integral of cosecant squared x is negative cotangent x, we evaluate negative cotangent x from pi over 6 to pi over 4. Step 2. Now we use the fundamental theorem of calculus. We substitute the upper limit pi over 4, then subtract the result when we substitute the lower limit pi over 6. This gives us negative cotangent of pi over 4 minus negative cotangent of pi over 6. Step 3. Now we substitute the exact trigonometric values. Cotangent of pi over 4 equals 1, and cotangent of pi over 6 equals square root of 3. So we get negative 1 plus square root of 3. Our final answer is square root of 3 minus 1. If we want a decimal approximation, this equals approximately 0.732. This completes our evaluation of the definite integral. The integral of cosecant squared doesn't just live in textbooks, it appears in real physics problems. One fascinating example is in analyzing pendulum motion with large amplitudes, where the simple approximations break down. For small angles, we use the familiar approximation where the period depends only on length and gravity. But watch what happens when we increase the amplitude to 60 degrees. The motion becomes much more complex. For large amplitudes, the exact period formula involves an elliptic integral. This integral cannot be expressed in terms of elementary functions, and here's where our cosecant squared integral becomes crucial. The mathematical connection starts with energy conservation. The kinetic energy of the pendulum bob equals the change in potential energy as it swings. We can express the velocity in terms of the angular velocity, which gives us this relationship between the angle and time derivatives. Separating variables to solve for the time differential, we get this expression. Notice how the denominator contains a square root of a cosine difference. The key insight comes from a trigonometric substitution. By expressing the cosine difference in terms of sine functions, we can transform the integral into a more manageable form. After this substitution and some algebraic manipulation, our integral transforms into exactly the integral of cosecant squared that we've been studying. Using our knowledge that the integral of cosecant squared is negative cotangent, we can evaluate this integral and find the exact period of the pendulum for any amplitude. Beyond pendulums, the integral of cosecant squared appears throughout engineering, particularly in Fourier analysis of periodic functions. This mathematical tool is essential for analyzing signals with sharp transitions or discontinuities. These mathematical concepts directly impact technologies we use every day. From the clarity of your cell phone calls to the efficiency of audio compression, the integral of cosecant squared plays a crucial role in modern engineering. This beautiful connection shows how a seemingly abstract integral becomes essential for understanding everything from grandfather clocks to smartphone technology. Mathematics truly is the language that describes our physical world. Now that we've learned how to integrate cosecant squared, let's address the most common mistakes students make and share some tips to help you succeed every time. The most common mistake is forgetting the negative sign. Many students write the integral as cotangent of x plus c, but the correct answer is negative cotangent of x plus c. Remember, the negative sign is crucial because the derivative of negative cotangent x equals cosecant squared x. The second common mistake is ignoring domain restrictions. Cosecant squared x is undefined whenever sine x equals 0, which occurs at integer multiples of pi. Here's a crucial tip. Always verify your integral by taking the derivative. If we differentiate negative cotangent x plus c, we should get back to cosecant squared x. The derivative of negative cotangent x is negative times the derivative of cotangent x. Since the derivative of cotangent x is negative cosecant squared x, we get negative times negative cosecant squared x, which simplifies to positive cosecant squared x, confirming our integral is correct. Practice with related trigonometric integrals to build pattern recognition. Notice how secant squared integrates to tangent, while cosecant squared integrates to negative cotangent. Remember these key points. Don't forget the negative sign, watch for domain restrictions, always verify your answer, and practice with related integrals. With these tips, you'll master the integral of cosecant squared x. Keep practicing, stay confident, and remember that mastering calculus is all about understanding patterns and checking your work. You've got this.